Hello, everybody. Good evening or good morning, according to where you are located. We're very happy to today to conclude the lecture series for the Advanced Architecture Contest lecture series on the topic of AI for the built environment. We're extremely happy that for this closing lecture, we have with us Jenny Sabin. She has been actually with us a month ago physically for the in-person responsive city symposium. But we're very happy to host her as well in this event, since her work is very relevant on let's say a new design paradigm in relation to architecture that is not only integrating technologies or AI, but as well as other disciplines and other species as well, including disciplines of biology and mathematics. Very short introduction for Jenny. She is an architectural designer. Her work focuses on combining architectural design, creative design with science. And she applies insights and theories from biology, from mathematics, with the goal to design novel spaces that they have novel behaviors, design of responsive material structures, as well as ecological spatial interventions. And she has been doing that at different scales, which is something very interesting when we experiment with this multidisciplinary approach in architecture. Jenny is a professor in architecture at the Cornell College of Architecture, where she also leads the Sabin Design Lab. But in parallel, she runs her own practice. So she's a multifaceted scholar and practitioner. She's the principal of Jenny Sabin Studio, and she always tries to connect the research and the experimentation happening in her lab at Cornell with professional work, as I was saying, at different scales. Jenny has been a designer that has impacted widely the way that we think behind research, and she has been showcasing her work in different places around the world. She has been in 2017 the winner of the MoMA PS1 Young Architects program that offers the possibility to build a one-to-one structure at the MoMA courtyard. And she has worked since then with a series of industrial partners and clients that had a vision of creating an architecture that is experiential, but it is also an architecture that, as I was mentioning, is able to take advantage of computation, of biology, of mathematics, of physics, of different sciences, to rethink not only how we design and build, but more than anything, how we inhabit our built environment. So I'm very, very happy to welcome Jenny Sabin. She will be lecturing on biosynthetic design and giving us hints of how we can work towards adaptive architecture. Jenny, thank you very, very much, as always, for supporting the activities that we are organizing from IX side.
Yeah, thank you so much, Areti. It's a real pleasure and honor to be here this evening, this afternoon, this morning, wherever you may be in the world. And it's just been really fantastic to connect over the last couple of months through the various programs that IAC is putting on, which are really truly at the cutting edge in terms of addressing some of the pressing questions and crises that we face globally and beyond. So I'm going to share my screen here.
Yes, please do so.
do you see
Yes, all
the
okay.
full
We can see
screen?
that. Yeah.
Great. All right. So thanks so much for joining. So in my talk today, which will encompass about 45 minutes, we'll have a bit of time for questions at the end and discussion. I will be arguing that technology, and specifically artificial intelligence, is fundamentally human, and that while generative AI opens new possibilities for the creative process and certainly uncanny new forms of ornament and beautifully complex formal structures, architecture has yet to really fully tap into the potential of AI to generate adaptive and personalized architecture for multiple species and environments. At the same time, AI has the potential to completely change, radically change existing workflows within architectural design, both pedagogically and also in practice. For example, computer vision and machine learning algorithms can be used to analyze any mistakes made during the construction process and to then improvise solutions on the fly. And through the design, steering, and crafting of big data sets, AI can offer new approaches to sustainable cities and architecture, to build smarter, and to generate empathetic and healing architecture through reciprocal engagement with our own changing dynamic biodata sets. And I'll talk about one specific project, ADA, in collaboration with Microsoft Research, where we explored some of those topics in depth. Used opportunistically, inappropriately, or maliciously, or even illegally, AI presents deeply problematic and ethical concerns around issues of bias, privacy, and entanglements with capitalistic power structures and big tech. These data present new forms of value that we are only just beginning to comprehend and understand, value structures that are driven towards capturing, manipulating, and using personal data sets for profit, from the stealing and plagiarizing of individual artistic styles to the strategic profiling of individuals through facial pattern recognition. Certainly, AI unchecked is and will continue to have grave consequences. So many of you are familiar with Imad Mostaq, the founder and chief executive of the startup Stability AI, and their now very well-known product, Stable Diffusion, and hero to many for releasing Stable Diffusion as open source a little over a year and a half ago. But as Kevin Roos, who is a technology columnist for the New York Times, wrote in reaction to this release in his article titled "A Coming Out Party for Generative AI, Silicon Valley's New Craze," which came out in late October of 2022, he states, quote, "If this all sounds eerily familiar, it's because Mr. Mostaq's pitch echoes the utopian dreams of an earlier generation of tech founders, like Mark Zuckerberg of Facebook and Jack Dorsey of Twitter, now known as X. Those men also raced to put powerful new technology into the hands of billions of people, barely pausing to consider what harm might result," end quote. So while the libertarian ethos and optimism towards the democratization of AI tools through open access should be celebrated, it is groundbreaking and incredibly exciting, to say the least. We cannot afford to be naive, or we are at risk of perpetuating entanglements of systemic misinformation, AI-generated propaganda, new forms of plagiarism, and persistent issues impacting diversity, equity, and inclusion. And many of these topics were discussed and debated during the 2020, 2021, 2022, and 2023 Acadia conferences. Now, take, for example, theorist and historian Amelia Jones, who underscores how neutrality is a problematic concept in design, and that the whiteness of tech and algorithm design, including AI, can perpetuate systemic racism and sexism as it frequently does not prioritize diverse users. She challenges us to consider how design can be driven by issues of access, inclusivity, and equity. And to do this, she offers some interesting methods and ways of approaching this. She argues that we need relational design strategies that foreground relationality and participation, and to engage and acknowledge the embodiment of the receiver, the audience, one's community, and to refuse the neutrality that has dominated art and design in the global north. Instead, she argues we must embrace connectedness and the engagement of broader communities. And she offers some very explicit methodologies for doing so, including cybernetics and generative strategies that are imbued with feedback loops, where the user and interaction are part of and are imbued with feedback between the user and their environments and larger networks of communities and users. Philosopher Benjamin Bratton, on the other hand, argues that AI is used for both smart and stupid things, and its ultimate purposes may be largely yet undiscovered. And he further underscores the presence of what he calls, quote, a sensing layer, and its promise to act back upon and govern itself. So, for example, to be excluded from testing in the context of the pandemic, and therefore being excluded from being sensed, is to not count, which equals exclusion. The data sets driving text-to-image generative AI largely privilege a Western paradigm of new image making. And AI is radically changing the creative arts and design landscape, and in many ways, design and technology have never been more important. Recent advances in computation, visualization, material intelligence, and fabrication technologies have begun to fundamentally alter how we design, how we make, how we construct across multiple length scales, from the nano to the macro. For example, how might we rethink building materials through 3D printing and biologically informed design? Can buildings be made more responsive through the integration of artificial intelligence and big data? These new intersections between the digital, the biological, and the physical are radically altering the world across multiple length scales. And so this afternoon, I'll present a working methodology and conceptual foundation that I've cultivated collaboratively across disciplines for over 18 years now. And I'll present two projects with a focus on AI augmented environments and also living matter or programmable matter. So in many ways, in the not so distant future, materials will cease to be elements and things in buildings, but instead will generate immersive and regenerative adaptive structures. So like the cells in our very own bodies, sensors and living architectural materials will learn and adapt, making materials not only smart, but also cyclically engaged with local environments and resources through ecological feedback loops. And this notion of dynamic reciprocity, specifically coming from biology, a specific set of biological models based on the extracellular matrix, which I'll go into depth in just a moment, has provided a series of very powerful ecological analog thinking models to bring back into design. And I'll touch upon this in more depth in just a moment. And this is a photograph that was taken on the first day of a course that I co-taught with a longtime collaborator, the late Dr. Peter Lloyd-Jones, who was a cell and molecular biologist. This course was called Nonlinear Systems Biology, Intersections Between Architecture and the ECM. And we taught it for 4 years, starting in 2007 at the University of Pennsylvania. And students from architecture, science and technology studies, medicine and engineering, engaged collaboratively in a hybrid lab and studio environment. And this sort of starting point and what ultimately informed Lab Studio that Peter and I co-founded in 2006, just before launching this course, really serves for a foundation of thinking and working a set of methods and tools that continue to drive what I'm doing here at Cornell in my lab, and also in how these concepts are being applied in architectural practice. So I believe and argue that to address today's pressing issues in our built and natural environments, that scientists, architects, and engineers must embrace change and cultivate new collaborative models to comprehend key social, environmental, and technological imperatives. This mode of working, which I call biosynthetic design, has contributed to a body of fundamental research and applied projects that integrate science, technology, and architecture through methods and tools that emphasize design research as a continuous and emergent process. So we frequently do not start out with a specific problem or application, but instead we develop a process, a way of working that allows for problems to emerge that we then, of course, solve. And this is one of the hardest things to teach to my students, but also it allows for an immediate bridge collaboratively with my scientific colleagues, because it's a way of working that's actually quite common in the sciences. So I'll touch upon this working methodology in a few different ways throughout my talk. So we're also very much interested in how these tools and techniques and methods can innovate responsive, non-standard building skins, bio bricks and tiles, and sentient spaces that are not only performative, but also generate what author Jenny Odell calls, quote, attention-holding architecture, end quote. For example, one of the fundamental questions that drives all of the work is how might buildings behave more like organisms do, responding to and adapting to their local built environments. We integrate the premise that nature is resilient, not efficient, into our thinking and processes analogically. And we also embrace transdisciplinary design with, as I've just mentioned, a focus on problem and knowledge generation over immediate problem solving through collaborative design processes that are generative and evolve over time with specific applications that result from that process. So with strong links to my lab here at Cornell, the sort of fundamental driving mission behind my practice and research is to create resilient, science-driven, and transformative spaces with and for diverse communities. And these are oftentimes sited in large urban environments. And as my friend and colleague Akam Menges recently stated in a conversation with some of my students, we need more research and practice and more practice in research. So this interest probes tinkering, the misuse of digital fabrication machines that are frequently found in other industries and disciplines such as medicine and the textile industry. And of course, this is imbued with issues of craft and making and messiness, of experimentation. I also like to sort of explore the potential of productive failures, taking advantage of process as failure in knowledge production. And this results in material systems and software design tools that hopefully have the capacity to facilitate embedded expressions in our built environments. So as I mentioned previously, a seminal reference for the work is the biological extracellular matrix. This is a dynamic protein network that physically and chemically couples the exterior environment of cells with their interior and vice versa. It's also a cell-derived woven and globular protein network that contacts most cells within the body. It's a type of architectural, dynamic, and adaptive textile of sorts. And so the big idea here is that half the secret to life resides outside of the cell itself, right? So you have DNA or code, but that DNA is acted upon by external environmental events. So the architecture of the environment through dynamic reciprocity influences and affects growth, morphogenesis, changes in geometry, materiality, program, history, event. So the level of intelligence and adaptivity through this dynamic ecology presented to us very early on, as I mentioned, a way of thinking and design that's incredibly powerful, but most importantly, relevant to the current questions and crises that we face. So I'll be touching upon this throughout the course of my talk. So this method of working across science, engineering, and architecture cultivates what I call a biosynthetic design process, where the generated results are materialized as architecture that hopefully are capable of responding dynamically to both environment and to deeper interior program systems. So with eSkin, which was an early 4-year research project funded by the National Science Foundation, which is a large federal funding entity here in the United States, our emphasis rested heavily upon the study of natural and artificial ecology and design, and especially in observing how cells interacting with pre-designed geometric patterns could alter those patterns to generate new surface effects. And we focused specifically on the topic of structural color in the form of adaptive thin films for building skins. And just as an interesting side note, this was a really important, big, multi-million-dollar grant for us to get, and this was in 2010. We had about 5 years of working collaboratively under our belts through Lab Studio, through the teaching, through advising thesis and PhD students, through exhibition opportunities, and built prototypes with material scientists, architects, of course, biologists, mechanical engineers, and beyond. And the program director for this specific call at the NSF said, you know what got you this grant was Lab Studio. The fact that you demonstrated through a new, unique model that collaboration could be possible across disciplinary boundaries. But it was a real game changer for us in terms of having the institution of the NSF say, this is important, this is the future, this is the way that we need to work, and this is the way that we need to approach the topic of sustainability. So through this, we explored concepts of personalized architecture, such as the promise of generating windows on demand or adaptive frit patterning at the scale of high-rise buildings. Some of you may be familiar with a typical strategy for reducing heat gain in high-rise buildings, which is to have static frit patterning on glazing, which limits the amount of UV entering the building, but doesn't block one's view from the interior to the exterior. And we thought, well, what if that was dynamic? What if it changed throughout the course of the day by integrating concepts of structural color and working specifically at a very fine scale with how cells were manipulating their local environments. So in contrast to biomimicry, biosynthesis fosters process-based research where design solutions and applications emerge in a shared collaborative space through bottom-up, materially directed, ecological, and systemic thinking and design. Running concurrently with this research, and this will give you a kind of view into how I navigate my lab and the team within my lab, within the institution of Cornell, and my practice, which is outside of Cornell. It's a business. It is a completely different team, but conceptually they're very linked, but are funded also in very different ways. So running concurrently with the eSkin project, I was fortunate to receive a commission from the College of Human Ecology here at Cornell to develop a permanent pavilion structure on Cornell's campus. And We were interested in how the project could integrate environment and community through, of course, the integration of advancements in computational design and digital fabrication, but also importantly, exploring responsive and adaptive materials that could ultimately inspire a space for pause, exchange, to positively interrupt one's day through the kind of concepts of wonder and community interacting together in sort of chance moments and events. So structural color in this case is achieved with a dichroic or wavelength dependent thin film that's laminated to tempered glass panels, which you can see a detail here. So in this case, light reflecting from and refracted onto the film changes color and grows warmer or cooler, more opaque or transparent, and is not based on pigment, but on how the film selectively interacts through interference or reinforcement of certain wavelengths of light at a microscopic scale. So a key component to the project is how we perceive these subtle to dramatic changes of light and color within the material itself. And this is just a view at night, and I'm really happy to report that this has become a really beloved project on campus and is highly frequented by both students, staff, and faculty as a space of engagement. And also experimentation. So in addition to designing at the architectural scale through demonstrator projects and experimental prototypes with responsive materials, we frequently design and fabricate environments that change and respond to dynamic data sets in real time. This is a project that we recently finished that's sited at the new Google Bayview campus, designed by the Bjorka Ingalls group, BIG, together with Heatherwick Studio in Mountain View, California. And these two projects are permanently installed within an open and adaptable structure at the Bayview building. So over the years, we have developed a way of working that is defined essentially by three formal phases to discern which effects and materials are actually scalable. We typically start out with the design of new tools, the design of scripts and algorithms to visualize and simulate behavior. These tools may be based on a specific mathematical concept or algorithm, or a material system, or a specific biological data set. And then we move those tools into architectural prototyping, and importantly, with a focus on feedback. And this is where we work with robotics and 3D printing and productively start to contaminate the process with aspects of making and architectural questions and constraints. And this is the sort of rub or point where we begin to grapple with scalability. Not all of the material systems that we're exploring, and this occurred with the Eastfin project, are scalable. And so we have to think about how specific characteristics and parameters that may emanate from a specific concept like structural color may translate across multiple scale lengths. And then some of those successful prototypes are then pushed into the realm of buildings and the built environment and issues of building ecology. And I would say this is where the practice arm of my work comes in, where we're really able to test tools and prototypes that have reached a certain maturation and testing. So in addition to innovating adaptive and responsive materials, we also work with non-standard components to investigate the rapid manufacturing of full-scale 3D printed parts for larger architectural assemblies. And I'm going to talk about just one project that engages living materials and live feedback loops between materials and their environments. This has led over the last decade to a series of seminars and option studios on the topic of digital ceramics. representing, as I mentioned, over a decade of work. We started experimenting with 3D printed clay, specifically in 2009. And in my lab, we kicked off a series called Polybrick. After a series of experimentations with clay, I thought the brick was a very accessible point of departure. And bricks really haven't changed a whole lot because of how they're made and manufactured. But as everybody knows, with the advent of 3D printing, every single brick can be different. One can begin to consider porous bricks, extremely lightweight bricks, the possibility of 3D printing directly on a construction site with multiple printers. And in Polybrick 2.0, we have turned to nature again. Here we've been exploring the mechanics of bone, collaborating with Dr. Christopher Hernandez, who is a mechanical engineer with expertise in the mechanics of bone. We think human bone is a pretty amazing model to explore, to optimize for load paths, but also to look at the promise of building with holes, kind of paradox of building with holes to generate incredibly robust but lightweight structures. And you see this everywhere in nature. So why can't we bring this into how we conceptualize bricks, the use of clay media, 3D printing, and applications that are scalable in architecture? So I'm going to linger a little bit on this project for those of you that were participating in the Responsive Cities Symposium. I touched upon this a bit, but didn't have an opportunity to go into much depth. So I'll linger on this for a bit longer. And this project, I started with Dr. Dan Lau, who's in biological environmental engineering at Cornell. He's really at the forefront of engineering DNA for programmable materials. So putting DNA to work as new types of materials that are responsive. And in addition to that, he has innovated a series of techniques for 3D printing DNA hydrogels. So these DNA sequences that have specific functionalities designed and engineered within them are then applied into these hydrogel substrates. And so we've been focusing on our work with 3D printed clay and digital ceramics as a substrate, as a ground for plating these new living glazes that have dynamic feedback mechanisms. So we went back down in scale at the starting point to refine the patterning and signatures that the DNA hydrogels would interact with. And we specifically focused on fluorescence and the emission of light in our first phase. So the prototypes utilize 3D printed clay, hydrogel, and synthetic DNA to explore programmable biofunctionalities in our constructed environments. So DNA, which is known as the information storage molecule for biological systems, is also a very known material for engineering. So it's synthetically designed. And again, in this first phase, we've been focusing on the emission of light. And so how have we done this? Specifically, we are working with a DNA sequence based on the luciferase, or the magical firefly. So the input energy in this case is ATP, and the output energy is light. So this enables cell-free production of light on ceramic tiles. And we actually had a lot more success in the beginning than Dan and I originally anticipated. And we have found that clay is actually an incredible host for life and for these successful engagement with these DNA living glazes. So with Polytile 2.0, what is most exciting is that we're working at the typical scale of an architectural tile, right? So we're working at scale. So we're no longer having to grapple with, okay, will this actually function and operate at an architectural scale? So the tiles integrate 3D printing patterning techniques, and the patterning and glazing that we do on the ceramic tiles is incredibly important in terms of steering how the DNA operates in terms of its programming and how it responds locally to its environment. So imagine a living wall that not only alerts you to local contaminants or particulate matter in the local environment through the emission of light, but then cleans that local environment through chemical and biological interactions. So this next phase of the work is starting to really dial in and program these active feedback mechanisms through local environment, specific proteins that the DNA and molecules that the DNA is interacting with the end goal of not only alerting you to those contaminants, but also cleaning that local environment. And if you're interested in taking a deeper dive into this work, we've published a number of recent papers on this, both on the scientific end and also on what we've been pushing on the design and architectural application side. And all of those papers you can find on our lab website, sabinlab.com. So this second and last project that I'll talk about this evening builds upon over a decade of work testing how these biologically informed concepts and adaptive materials can be applied experimentally in architecture with and for diverse communities. And specifically, our work in artificial intelligence has focused on the following two questions that you can see here on this slide. So since 2012, we've been able to deepen and apply our ongoing research on responsive materials that engage the dynamics of light and energy, such as structural color, but through high-tech solar active and photoluminescent responsive fibers. And this commenced with the MyThread Pavilion for Nike in 2012. So here we're taking the same concepts, such as structural color, the promise of programmable materials into a new type of fabrication and manufacturing process, engaging the textile industry and specifically knitting, and working with high-tech responsive fibers as a way of programming those behaviors. Following several projects from that initial project, which also resulted in a really robust collaboration with Shimashiki. They are at the forefront of what's called whole garment knitting, which is 3D digitally seamless knitting. And we've been working with them now since 2012. Some of the projects have included polythread for the Cooper Hewitt Design Triennial. And we were able to take this work to an urban scale with our winning entry Lumen for MoMA and MoMA PS1's Young Architects program in 2017. And this project featured over 18,000 square feet of digitally knit porous canopy structures. This is a view from above at MoMA PS1 in Long Island City in New York. The project also featured 3 dynamic 42-foot tall tensegrity towers. You can see 2 of them in the main courtyard here, as well as an interactive misting system, robotically wound stool spools that were made from recycled and deconstructed cable spools that were then rewound robotically with a photoluminescent fiber. And for the very first time, we were able to test our high-tech responsive fiber knit material system with actual context and the changing conditions of the path of the sun. I'm not going to talk about Lumen in depth, but just to give you some of the highlights that have contributed to ADA, which is the project that I'll end with. So we worked with the existing matrix of concrete walls at MoMA PS1 as a set of constraints. Here are some details of those large tensegrity towers. And so the whole project was designed and engineered and materialized to be highly dynamic, both in how materiality is co-produced between people and the community that engages the project, but also specifically how the materials interacted with the changing conditions of the sun in terms of the photoluminescent fibers emitting light, dynamic switching of color in the presence of UV, and also the dynamics of the misting system. And here are some images taken on a given Saturday, which was called Warm Up, where these large public events would engage amazing DJs and artists who performed. And Lumen was loved by upwards of 7,000 people on these Saturday events, and actually held up quite well over the course of the summer that it was up and installed. And in a recent project for a really innovative developer in Imcan in Abu Dhabi, we designed and produced a permanent public beach activation project. Abu Dhabi has, in the last 5 years, put a lot of investment into public space, which if you have been to the UAE, public space does not exist really to a great degree. And so we collaborated this time with Gore, who produced Gore-Tex, you're probably familiar with their clothing, to develop an entirely new photoluminescent ePTFE material that could withstand the extreme climate of Abu Dhabi, including sandstorms and windstorms. And this is another image taken of Lumen on one of those Saturday warm-up days, where you can see just the sheer crowds that gathered. So our collaborative work also includes a significant human component, both in how it's made through a hybrid of analog and digital design processes, and also through the active engagement with communities in urban contexts. So Ada, my last project that I'll talk about today, which is by Jenny Sabin Studio, my practice, was in collaboration with Microsoft Research. I was fortunate to be invited by them in 2018 to serve as their artist and designer in residence, which was an extraordinary experience. We were, from the very beginning, interested in exploring the possibility of developing a project that would integrate artificial intelligence, but explore the ethical issues around the use of AI, aspects of privacy and bias, and ultimately to look at a side of AI that could potentially be fundamentally human, to open up the technology, to make it more transparent, to make it accessible, and also for it to be directly integrated into a dynamic environment that was constantly changing. Which goes back to some of my initial topics and arguments that I presented at the start of my talk this evening. So in many ways, a transdisciplinary practice can provide collective and democratic solutions to important questions around technology and big data to enable new forms of access, well-being, and agency. And so I think collaboration across disciplinary boundaries is a way of opening up not only these questions, but effectively navigating them. So we've been exploring, and specifically through this collaboration, how artificial intelligence can personalize rooms and buildings. And I'm just going to play this video in the background and won't play the sound, but just to provide some dynamic visuals of the project. In many ways, the spaces and environments that we inhabit influence and feel how we act, right? Our environments affect us. And so working with Microsoft, Ada is driven by individual and collective sentiment data that is collected and housed within the Microsoft Research Building, which is located in their Redmond campus in Washington State in the US. The project is named affectionately after the polymath mathematician, first computer programmer and early innovator of the computer age, Ada Lovelace. And we were interested in how the project could embody performance, material innovation, and ultimately what could be a human-centered or species-centered adaptive architecture. So we've been told that Ada at the time was one of the first architectural pavilions to incorporate AI. And so the lightweight pavilion, just to give you a little bit of background, this is the brain ring, a view from the top, is composed of responsive and data-driven tubular and cellular components. So again, building upon all of our robust work with digital knitting and soft textile-based material systems. And this is held in continuous tension via a 3D printed semi-rigid exoskeleton, right? So there's reciprocal forces operating equal and opposite to each other. The external rigid shell structure is composed of just under 900 unique 3D printed nylon components. And the lighting system and materials respond directly to human participation as individual and collective facial pattern data are collected and transmitted as sentiment through light and color. And just to give you a little bit of detail on the architecture of the software, essentially, we programmed the software architecture for two programs, which allow Ada to interface with human sentiment in her environment, which is a program running on an on-site PC and a program running on each of the Raspberry Pis within the brain ring. And here's some diagrams just highlighting the material system. So a really important aim of the project was to expand and inspire architectural engagement through the use of AI. And so while AI powers the project through the precise and very statistical averaging of data collected from individual and collective facial patterns and voice tones, the architecture and the materiality of Ada offers an aesthetic experience, which thereby opens the possible range of human emotional engagement, right? So this direct reciprocity between our own human biodata sets and how that is reflected back through the architecture, through changing conditions within materials in the environment, was ultimately what we were really fundamentally interested in tapping into as a set of possibilities, right? As a demonstrator of what could eventually become architecturalized at a building scale. And this also goes back to this notion of dynamic reciprocity that I talked about at the very beginning of my talk, that was informed by my over 8 years of investigation into surface design within the extracellular matrix environment. Just a few more details. This was the center of the project. There was also a camera you can see here at the center that could override all of the other cameras within the building. So someone could directly begin to influence the project by inhabiting the pavilion, which was really great to see sort of people's discovery of that on the opening night. So in this way, personalized architecture has the potential to sense subtle changes in human emotion through sensors and interfaces that detect changes in our own facial patterns, changes that we may not even detect, which Daniel McDuff, who was my primary collaborator on the AI side, has been exploring through his work, and specifically within populations of the elderly and seniors, and thinking about how this technology can give us some clues as to what's happening in our environment that's impacting our own wellness and health. And we think that's a pretty amazing way to start to think about adaptive architecture and the use of AI and the ethical use of data sets that can be anonymous. And all of this, one could opt out. All of the data sets are anonymous. There was no capturing of individual data sets. But we do have an archive of any given day. So one could ostensibly look at the sort of mood of the building and how that changes over seasons, from winter to spring to fall and beyond. So in this way, Ada offers subtle and abstract interactions with humans through both space, material, and form. And here are some photos taken on the opening night when people realized that by exaggerating changes in their facial patterns, they could then in turn immediately change the responsive materials and materiality of the project. So through the integration of responsive materials and emerging technologies, Ada hopefully offers, as a demonstrator, an interface for personalizing architecture to make it more human and reflexive. And at the same time, Ada expands human emotional engagement through beauty and materiality. It's a demonstrator project that showcases the capacity and future of architecture to promote and increase well-being through the direct engagement with the spaces that we inhabit. And I'm happy to report that it's now still, permanently installed. It's being used as a research platform. When we designed the software architecture, we purposefully made it very open and parameterized so it can receive any data set. So this allows for researchers at Microsoft Research to probe into data, to look at it in different ways, and how, through the interface of Ada itself, right? Through the spatialization of the data, essentially. So to conclude, transdisciplinary design is about connections and synergies across science, technology, and architecture, steered by the systemic and relational conditions of life, from DNA to sentiment, as future adaptive and intelligent materials, and the optimism of possibility. We've been fortunate over the many years now to receive a lot of support, both at the institutions that I have been fortunate to teach at, but also through industry partners and federal funding agencies such as the NSF. And of course, we are a we. I could not do any of this without my collaborators, without my students, without my research associates, without my senior designers at JSS. And I've highlighted just a few projects. There are many more. This is where you can find us. As I mentioned, all of our published papers, for the most part, are downloadable at sabinlab.com, and you can see what we're up to in the studio of my practice at jennysabin.com. So with that, I think I'm just 2 minutes over, which is great. I will end, and I'm happy to take any questions that you might have. Thanks so much.
Thank you so much, Jenny. Thank you for a brilliant talk. I always feel that each of the projects that you have been researching and working both in your lab at Cornell and in your practice is a scientific innovation, a PhD in itself, or various PhDs. And still it's architecture, no, and it's a complex, impactful, sensible or sensitive, as you say, architecture. And as I was saying in the introduction, I think that this diverse work that you have presented today is contributing also to a necessary, or better said, an urgent reflection that we need to do on the way that we design and build, and on the way that our built environment behaves or operates. No, we are definitely moving towards possibilities of creating, as you say, environments that they are closer to living organisms rather than static and rigid structures that follow Cartesian grids and principles of standardization or repetition. And this necessary reflection is, on the one hand, how built environment could actually become responsive to the environment that surrounds, to the different inputs, to the different species, how it could affect positively the environment, but also how it affects positively the society. And then I am really interested on the fact that this opens, of course, there are a lot of questions in relation to how this could become a building, or what part of a building is this, but I think that it definitely introduces as I was saying, new inhabitation models and also relationships between the built environment and the inhabitants, relationships of empathy, relationships of care, rather than the traditional way of thinking of maintaining a building. No, we are moving from ideas of maintenance towards the ideas of care and coexistence, and I think that is definitely opening up great possibilities, not just on the material or technological and design side and computational side, but also on the philosophical and cultural side of how we inhabit, especially at a moment that we need to respond to multiple crises. Anyhow, I just heard some thoughts loud here, but yeah, this is basically to say thank you. And yeah, I would also like to open if there are any questions from our audience. I see that Maria Isabel, you can also open the chat, Jenny, if you wish, but she's asking what is your vision of design for the future and what materials are the ones that comes next, or the ones that we will use in the future.
Thank you, Areti, for your really excellent summary. So the question, what is your vision of design for the future, and what materials are those of the future? So hopefully I was convincing through my talk that I really think that the model for design and how we design absolutely needs to be collaborative across disciplines. And I think we're seeing increasingly a strong need for designers and architects to step into these spaces. We're really good at devaluing what we have to offer, right? And in terms of the way that we think synthetically, our ability to work across a range of complex parameters and relationships to formulate a plan, a path forward, and to, direct and choreograph and work with multiple people, whether it's people in industry or other disciplines. And I'm very thankful that this sort of myth of the architect as a sole author is disappearing. And if we're not proactive, if we, especially in architecture and engaging these new models for practice, I fear that the role of architecture will increasingly become more obsolete. And we have I think, a really amazing opportunity to upend our conception of what practice is and what research is, to integrate them together, and to step into spaces that may not be comfortable, to go to lectures and other disciplines where you will have to let a lot of information sort of slide over you, but really believe in your disciplinary core and what you have to offer and what you have been trained to do. But work with other colleagues, work with biologists, work with material scientists. I really think that it's not only the future, it's the now. And that's how we're going to address the pressing issues that we face, whether it's climate change globally, or issues of access and equity that impact social and political and cultural contexts. So that I have a lot of faith in that, and it's not easy. I have been developing this model of working across disciplines for 18 years now, and I'm thankful that there are many more colleagues now engaged in this, but it can oftentimes be a lonely path. But I think the first step is to push yourself into other environments that are not just filled with architects, but other colleagues and potential collaborators that you could work with. In terms of materials, I'm blown away by what my colleagues in materials science and nanotech are doing in the context of living materials and programmable matter. Materials that not only respond dynamically to environment, but can change shape in changing contexts, pluripotent materials. So the possibilities are endless. Our limitations, I think, actually are in the areas of architecture, contracting and construction, litigious issues in terms of legal issues, building codes. In the States, we're working with building codes that are from like the 1960s. So there are a number of hurdles that we need to get past in our own fields that touch construction and building and codes that are limiting, I think, the real innovation that could be happening. Because what's happening in the lab is we won't see in the built environment for probably 20 or more years. But as I mentioned, I really think the future of materials and architecture will be much more immersive and dynamic, and no, buildings will not be moving. We don't like buildings that are constantly moving, right? But the materials and the interfaces that we engage with, I think, will be much more highly dynamic.
Great. We know though the limitation of scaling up on materials, that they're dynamic and active and smart. And but as designers also, we should be creative on how scaling up happens, rather than trying to just size up a performance, how extract the principles of the material and how we design with that. I think this is also something that in your work we could see, like from discretization to scaling up through smaller components that connect to central cores, let's say, of operation. There's another question from Pablo, although he somehow says that partially you have answered it. A question on how do you think that the adaptation of design and production methods more intertwined with biology and technology could be in the private construction market? How this adaptation could be in the private construction market, and what necessarily must happen in the next few years from your point of view? I don't know if that also implies, what kind of business models could be found around this kind of novel ideas and processes.
Yeah, really great question. And I think the key answer is collaboration, again, between what's happening in the lab, what's happening in research, and how that can impact practice and construction and innovation as a dynamic back and forth. And I think the models that have successfully achieved that are doing some of the most amazing work. We just actually literally 2 days ago learned that we've been awarded a new big grant. I can't talk about any of the specifics, but I can mention that what's most exciting for me is that we will be working directly with an industry partner that was a contingent on part of the award. And so that pushing each other, right? And us bringing the innovation and like what we're doing in the lab that's highly experimental, and our industry partners saying, well, this is what's possible now, let's work together and see how we can upscale manufacturing processes. And so I think collaboration across industry, practice, and research is absolutely essential, and going after funding models that allow for that to happen. I think some of the innovative practices that I admire, one comes to mind, and this is again touching upon the construction industry. There's actually local to Cornell, an interesting outfit called Construction Robotics, and they are very strategically pairing masons who have incredible body of knowledge around masonry work and construction and building and making with experts in robotic fabrication, with the knowledge that you can't replace one with the other, right? You need to bring the two together and to really push boundaries. So those types of collaborations, I think, are really exciting. Also, where you bringing knowledge sets that are maybe they share a material system, but they're coming at it from a very different sort of context and background. So
Great.
That's what we're trying to do. I mean, there are other answers, I'm sure.
Thank you, Jenny. Congratulations for the award. We're really looking forward to know more about it. Joanna is asking, whereas you see there is some limits we could or we should draw as the technology evolves massively, and whereas society might be even ready and accepted for this.
Yeah, also really excellent question. I mean, you have seen through my talk how we have approached the topic of AI and the ethical use of AI and big data sets. I think this is well, as I articulated in my arguments at the beginning, a really not only just obviously a hot topic, but one that, oops, I lost my screen here. You see me okay still?
Yeah, all okay.
Great. So I think, one, as a designer, one needs to approach these topics sensitively. Again, I think the key is collaboration to understand, what your disciplinary core is and the areas that are not your disciplinary expertise, and to locate collaborators that you can work with to address some of these bigger questions. And I think AI is obviously a big one. I'm, to be honest, surprised by what's not happening yet in architecture with AI. And image making has a long history in our discipline. And as I mentioned, the tools that we've been really pushing with generative AI are incredibly exciting, but there's so much more that can be done with how we craft and design and steer specific data sets to engage with larger environments, that are not about image making, but really designing with phenomena that we've never been able to work with before, right? And AI has the potential to allow for that bridge. So I think there's a lot that our discipline can tap into through collaborations with experts in computing and information science and engineering and software design that could really, really push the boundaries of what a living architecture and adaptive architecture might be.
Thank you, Jenny. I think that is a great way to close this lecture also, because along the different lectures of this series, we have tried to invite experts that deal with AI from different disciplines and different perspectives. And I think that understanding that the potential of AI could radically expand, let's say, the parameters that we can add to architecture so that architecture can become more alive is a unique vision and a powerful one. I really want to thank you for joining us and for sharing your work. Thank you everybody that has joined us and the ones that they have followed us on streaming. The video presentation of Jenny would be uploaded in the YouTube channel of IAC, and you can always come back to see this brilliant work. Thank you very, very much, Jenny.
Oh, thank you so much, Reti, and thanks everyone for joining this evening.